for the lunch.
Hello, everyone. So I think we will get started with the next session. I think people are still joining in after the lunch break here in India, and I'm hoping that folks back in the UK also have started joining. Just checking like if all the speakers are here. So we have Kuniko and Dr. Rameez. Great. I think Taofiq is not here yet, so I'm hoping he will join soon. And I was told Mr. David will not be able to make it. So, and Krishna is in a class right now. He should be joining us soon. Okay. So I think without further ado, I'll get started. So let me welcome Ms. Kuniko Paxton. She's a PhD student in data science at the University of Hull. She has had quite a bit of experience in the industry and currently working on safety and trustworthiness in AI and also a bit on healthcare. So Kuniko, over to you. You have 15 minutes and 5 minutes for Q&A. So when it's like 13 minutes, I'm going to just raise my hand.
Yeah.
Thank you. Go ahead.
Yes. Thank you very much. Oh,
So you are a co-host now, so you should be able to share
it's
your screen.
share. Okay. Yeah.
Yeah.
So share this one. Can you see my slide?
Yes.
Okay. Yeah, thank you. Hey everyone, I'm Kuniko Paxton, a PhD student at the University of Hull. My supervisors are Korush and Devar and Yanis. Thank you very much for supporting me always. And today's topic, evaluating fairness and mitigation bias, skin color in machine learning using Tensor data. So the contents is here. So the introduction, I'd like to introduce a history of AI fairness studies. I want to divide three terms. In the early terms, the unfairness in AI was discovered and they quantified and they created a group fairness definition and a mitigation system for that. The second term, we see some challenges, sensitive attribute categorization, individual fairness assurance, and the tabular data domination, and the conflict of fairness definitions. And the latest era, the demand for fairness became more sophisticated and subdivided the equity rather than equality. So preference, ranking, personalization, and robustness to uncertainty and to adversarial attacks and fairness explanation. So among them, we'd like to focus on yellow colored aspects, and I want to say reason why. So sensitive attribute is characteristics is to be protected from discrimination and harassment by law and regulation and guidelines. We divide it into three categories. First one, categorical. So the most of sensitive attribute belongs to this one, like gender and nationality, marital status, men and women, such like that. And then second one, continuous numeric sensitive attribute. This one is a scalar, so age, income, and so on. The last one, this one is new, and we'd like to introduce the tensor. So like a race, skin color, eye color, and the hair color. In a computer vision image data, tensor data. So here, the research gap. Traditionally, the skin color has been grouped into skin color types. Fitzpatrick 6 color type, moon skin tone 10 types. But here, difficulty, even experts cannot have consistency of the skin color scales because everyone has different skin color. And another one, a mixture of ethnic groups, white, black, Asian, and so on. But actually, race and ethnicity is different. Race is more physical traits, but ethnicity is a cultural identification. But now they are mixed up to use alternative of the skin color, good skin color. So, and this ethnic group tend to be selected based on the preference or situation. So it's very subjective. So here, group fairness and individual fairness. Now, group fairness is prioritized because of social requirements. So here, four requirements are law and risk of encode human, moral, shareable. So group fairness is important, but please think about skin color. We have variety of skin color, no one same. So in that case, definitely within the same group, we see the minorities. So minority within group should not be ignored either. So we need to fill this gap. So another gap, fair explanation and robustness. The fairness is a vague intuition. So people change judgment and justification the based on the circumstance and the explanation. And the counterfactual scenario, so people tend to think about if my skin color lighter or darker, if the changes skin color and the outcome different means there's a bias. So, and so far the statistical group fairness, it's outcome oriented. So basically, from outcome, we compared each groups, which one is of higher accuracy, which one is a lower. So it means we didn't focus on model behavior fairness. And then another one is robustness bias. Actually, their vulnerability depend based on the skin color. And the adversarial attack possible target particular skin color like Asian. But unfortunately, the explanation and the fairness and the robustness and the fairness, the study is not limited. So we'd like to work on that. Here, our objectives. So we propose a new fairness assessment framework for individual fairness within groups. The sensitive attribute is Tensor, case study skin color. We propose bias detection and mitigation for individual performance fairness of Tensor data. We create algorithm to identify model behavior bias using explainability and a counterfactual method. We identify the robustness bias to adversarial attacks and create defense system. So here is a redefined fairness assessment framework. We don't focus on only performance, but also explanation and robustness to adversarial attacks. And we use major metrics for the performance accuracy, the explanation, coverage estimation, robustness, attack success rates. So, but in this talk, I want to focus on only performance because of time. This one is our core method, how to calculate skin color, individual skin color. So the firstly, this example, skin lesion image, and we masked skin lesion area and to identify only skin area. And we calculate individual typology angle ITA values. This one is equation for pigment color. And we calculate this value each pixels. The conventional studies makes it average and convert it to skin color type, but we don't do that. So we make it distribution. So the red color distribution, this one is a base skin color, the photo we can see. And the gray color, this one is 100 samples. So of course, we don't have completely same distribution. So we compare the distribution and the distribution using a statistical distance metrics. So here, methodology to identify, detect bias and mitigate bias. Firstly, we train with base training model. This one is a pre-trained general model, no calibration for the bias. And the outcome of that and the skin color distance I introduced in previous slide. We use logistic regression to calculate probability of accurate data and the skin color distance. So we see the magnitude of the slope. This means a relation skin color nuance impact on the accuracy. So afterwards, we create kernel density estimation as an estimator. As everyone knows, the machine learning, the majority gets better, higher performance, but minority receive lower performance. So we identified the majority area and the minority area using the density of the accurate the predicted data. This density used as a penalty of the loss function. So fair training, we assembled a kernel distance estimation and to reweigh as a density as a penalty. So this one is experiments setup data set. We use ham data sets. And it's actually the 7 class classification. But because of data set limitation, we use 3 classes. And the model are relatively new 3 models are LessNet, DenseNet, and MobileNet. Actually, the average the performance is not so high. Even use a pre-trained model, the data set is very small, so cannot reach to like a 90. And then we need to simplify to see how color impact on the fairness. So more focus on that. So this one is a result, accuracy kernel density estimation. That depends on the characteristics of the statistic distance metric. We see the different shape, but we can see the area, high density and low density. So another result is this one. Blue colored one is a base training, and the orange color fair training. So I'd like to introduce Anderson distance case. The dense net and mobile net, we see the big drop down because of the color. But the fair training, the probability is almost flat. So score was 0.0369 to 0.0071 and 0.076. So this one is the became fair. So another version, this one is applied for the human image as well. And the difference between the kernel density estimation and this one, we use estimator Bayesian regression network. And the matrix was not only accurate data and the F1 score, but to use F1 score, we needed to make small batch instead of ultimately individual fairness. So here summary, skin color has unique characteristics, Tensor data set, and it has a nuance. Group fairness is essential, but individual fairness within group should not be ignored either. Fairness requires explanation, model behavior, and robustness by us, not uncovered yet. We need to address that. Our new fairness assessment framework for individual fairness within groups is multi-prospective, performance explanation, and robustness to adversarial attack. And our novel individual fairness training was demonstrated. So future work, we'd like to apply the 3D image, our methods, 3D image classification, image to image generative AI model, and the federated learning. And fair coverage estimation, validated using the gradient basis. It's like a GradCam or SideG map, and the local explanation like lime and smile, and the sharp with sharp, and the width and without counterfactual scenario. And we create fairness robustness defense to adversarial example based on the observation and the published below. This one is the relationship skin color and vulnerability to the adversarial example. And here's a reference. And thank you very much.
Yeah, thank you, Kuniko. That was a great
Yes,
presentation. Yes. So we
thank you.
already have a question on the
Yeah,
chat. So
yeah.
we have a question from Bhupender Kaushal.
Mm.
Uh, so if anyone else have questions, please do post it on the chat while we answer this. Which specific property of the tensor algebra you have utilized to classify your samples? If you care to address that, Kuniko.
This one is a tensor data set. This one is firstly the converted matrix. And the classified sample, maybe this one is the for the base training and the classified sample means like a logistic regression. Yeah, the focus on coefficient, so didn't check how much we have. The
Sure, sure.
mm,
So,
the
Bhupinder, if you
weight.
have any follow-up questions on that, you can chat. Meanwhile, I have a question.
Mm,
So, the robustness bias which you are mentioning, I know you have not
yes.
addressed that yet, maybe on the words, but uh,
Yeah.
what is exactly the poisoning attack on fairness? Could you maybe expand that for the group? Like, could you maybe
So,
give an example of what is a poisoning attack on fairness?
okay. So, so the adversarial example, like there's a noise or the gradient basis noise also, and if we put in that's our normal image, and then easily the model misclassifies. So and then using this the adversarial image, how much we can the model possible to classify the same as normal image. So, and then skin colors difference, and then that success ratio of the attack is different.
Right. Okay. Okay. So I think there are no more questions, but I will ask one more.
Yes.
So the what was the motivation for just considering the skin color?
Skin color is how to say the very controversial topic in a
Right.
society, and
Right.
yeah, and for the centuries it was discussed, but still not identified, and it's kind of carried over to the machine learning. So yeah.
Yeah, so I was wondering like if there is a motivational
Mm,
study from some social science background that actually can back you up with this, right? So
mm,
that could be maybe
mm,
I mean history says it all, but still,
mm.
yeah,
Yeah.
for a technical motivation we could have something like
Uh,
that. Yeah.
so
Okay.
yeah, the tense.
Sure.
Yeah.
So
Okay.
thanks, Kuniko. If
Yes.
there are any more questions in the chat, so please try to address them when you have time.
Yeah.
So we will move on. So thanks, Kuniko, once again.
Yeah. Thank you very much.
Uh, so Dr. Rameez, hope you are online.
Yeah,
Yeah,
I'm just
yeah,
trying to
yeah.
figure it out.
Okay. Okay, so let me welcome Professor Rameez, who is currently a lecturer and program director of the Hull Online MSc in Artificial Intelligence course in the University of Hull. He has expertise in the fields of AI, data science, edge computing, cybersecurity, and IoT. So, Dr. Rameez, nice to have you here in Chennai. Please,
Sorry,
thank you.
my MacBook is not allow me to share my screen.
Sure. Yeah.
I
If
don't
you
know why.
find that your network is bad, you can maybe turn off your video if needed.
Okay, let me just do that. Well, it's not issue with them. It's about MacBook. It's not allowing to share my screen.
Oh,
Just give me a second.
okay. I was just checking if you are co-host. Yes, you are.
Can you see my screen?
Yeah, it's coming up. Uh, okay, just I started sharing, but I can't see your screen yet. Mm,
So there might be some issue with the Mac. Now can you see?
Can anyone else see the screen? I cannot see it.
Just black.
No, it's all blank.
Yeah. Okay.
Maybe Ravi, if you can say, oh yeah, it's
Oh
Ah,
yeah.
coming.
Now it's here.
It's
Yes.
here.
Yeah.
yeah, can you see?
Yeah, we can see it.
Okay. Sorry for this delay, and thank you, Google, for your kind words and introducing me. So, good morning. Sorry, not good morning, actually. Good afternoon, everyone. My name is Dr. Rameez Kureshi, and I'm here today to present my research work around the Indoor Urban Observatory, using with the AI and IoT technology to drive the positive behavior change. Well, this work addressed critical issues in the indoor air quality domain and explored the innovative solutions at the intersection of technology and the human behavior. Well, I appreciate your presence and the attention. So let's begin. Okay, so Indoor air quality, short name IAQ, has increasingly become a significant concern for the health and well-beings, as we spend majority of our time indoor environment and doing various activities. The major factors influencing the air pollution in the residential and commercial structures are complex and multifaceted, as we all know about this. These include the activities we are doing, day-to-day routines, and building materials or the paints in our buildings. So addressing these challenges required a nuanced understanding and a multidisciplinary approach, forming the basis of this research, especially in the indoor activity context, right? Okay. So, sorry, I'm taking time because I have a dual screen and changing it triggered the problem. So that's fine. So how does we address these challenges? There is a cocktail solution proposed by the WHO for the air quality guidelines. And as you can see, they suggested some of the guidelines about the improving the air quality, promoting the cooking stove, how we can use it. But my main focus for this research is about how we can improve the people's awareness, how we can raise awareness actually. So for this, we have come up with the real-time monitoring solution, changing behavior and spreading awareness among the citizens, right? But how we can achieve this, that is another challenge, right? So how does the real-time indoor air quality data influence the citizens' behavior? So we work with the real-time monitoring. We have used the low-cost sensors, right? They are cost-effective, compact, and portable, and you will get the real-time data with the special temporal data, right? For the behavior, we focus on the how we can disseminate the information among the citizens and how we can educate them, right? But when we use the low-cost sensors, there is a problem with the low-cost sensor about the data quality, their performance, their data accuracy. Similarly, when we talk about the changing the behavior, the problem with the citizen engagement, that is the biggest challenge we have come across while we are conducting the studies. Awareness and the knowledge gap they have, because during the study we found out that some of the citizens they have the knowledge about the air quality, some of they don't have, and sometimes they have the issue with the technology, what the technology they are using, right? So that drives the 5 main important research question for our research. So the first one is how, if we use the low-cost sensors, how we can calibrate it. When we use the low-cost sensor for the air quality monitoring context, right? How we can monitor the data and show them in a way that they will get a positive message and that influence their behavior, and also that trigger their indoor activities, and from the indoor activities they can control their indoor environment, right? So these are the 5 research questions we come across, which I'm going to discuss in the next couple of slides. So starting with the sensor calibration. So we have used the 3-step approach. So there are lots of low-cost sensors available in the market. So for this research, I'm talking about just only PM 2.5 and PM 10, which is the particulate matter. People who don't know about the particulate, these are the very tiny particles, right? And that causing a lots of health issues. Okay, so for monitoring that, we have selected a couple of candidate sensors among what are available in the market, right? So once we're done with the candidate selection, sensor selection, we use the statistical techniques to further narrow it down. For example, there are 10 sensors. How we can narrow it down that these sensors have the data quality good, these are the accuracy is high, right? So we use the statistical technique to further narrow it down. And finally, we did the sensor calibration using with the machine learning models, which I'm going to talk in the next slide. Okay, so we have applied four, actually more than 4, but we finalized with the 4 machine learning models, right? MLR, MLP, CNN, and random forest. And we have we done the calibration of our particulate sensor, which is the STS011. We have choose 2 different UK sites. One is from the DEFRA and another one is the UK Urban Observatory from the Sheffield, right? And we found out that the random forests have the better calibration, which is the high accuracy. We got it. So we use the random forest, we calibrate our sensor, and then for the monitoring and indoor air quality, and then we have built up our sensors, right? As you can see in the picture, this is the device we have built up, right? We have used the different air quality monitoring sensors, temperature sensors, right? But the main focus was on the PM 2.5, PM10, which is the SDS011, which was calibrated, right? And then we have planned our studies that for the initial questionnaires to know the context, how our participants are living in their life, day-to-day routines, right? Before the study and after the study. That's why the initial question was the important part. Then we asked them to fill the daily activity log. We at the completion of the study, we interview them. It was a semi-structured interview. It's like a more conversation. So based on that, we have analyzed the data air quality. We have analyzed their behavior. We have asked their interview questions and the impact of technology on the citizen behavior. How we can use the technology to influence citizens' behavior so that they can improve their indoor air quality and same time they raise the awareness about this indoor air quality. We have used the COMBI model. It's a psychological model. COMBI stands for capability, motivation, opportunity. So for example, any person, if have the capacity to change their behavior, if we can provide a motivation, do they change their behavior? And if they get an opportunity, do they change their behavior? Like, so we use this model and we have designed the digital interventions that can help us to understand how we can disseminate the information so that they can get the best out of it and change their they can have the positive behavioral change for the improvement of indoor air quality, right? So for the indoor urban observatory, we have designed like we have conducted altogether 4 studies, right? But every study we do some sort of enhancement. So this is the dashboard we show them. As you can see in the figure, we show them PM 2.5, PM10 compared with the guidelines issued by the WHO and the UK government, right? So they can see the average of the indoor air pollution level among their houses, right? And these are the digital intervention we have designed. For example, showing them the indoor air quality data, showing them the information about how they can improve it, filling the daily activity log. These are the sample questions we have asked them. We have designed those questions based on the literature. And we also provide them the information about the improvement of what steps they can take to improve their indoor air quality, right? But during that time, in 2 studies, we found out that there is a positive impact of the indoor urban observatory. We have observed that among the studies. But later on, we realized that what digital intervention have the significant impact on their human behavior, right? So we use the Google Analytics and the Google Tag Manager. So we embedded with our indoor urban observatory, right, and see the behavior of the user on the dashboard, right? What the intervention they spend a lot of time, or what intervention that was there was not that much effective, or where they are spending a lot of time to understand their indoor air pollution. So based on that, we found out that with the data we collected from the Google Tag Manager and Google Analytics, that we did the sequential individual sequence analysis for each participants, overall sequential analysis across all the participants, user navigation pattern, from which intervention, from login to log out, which interventions they are moving towards, right? And the user engagement duration, as I said, what intervention they have spent quite a lot of time, which intervention doesn't have the spend, they have very less time they have spent, and the user persona analysis. But out of that, I'm just going to discuss only one about the user engagement duration analysis. So as you can see from the figure, the IAQ visualization, which shows their indoor air pollution level in their houses, right? So they have spent a lot of time, whether you see the individual or the overall. So the 5 digital intervention we have introduced to them, among 5, only the one which I mean, all are useful, but they want to know more about their indoor air pollution. For example, some of the testimony they said during the after the study, they said that whenever they feel smoke or they feel like there is something fishy in the house, they straight away open the dashboard and see the pollution level, right? So that helped them to understand their own indoor air pollution levels. Okay, some of the result I would like to discuss with you. So the structure of the study is like, it was a 3-week study. First week, we haven't give them any sort of information. Just we deployed our IoT devices among IoT indoor air quality monitoring devices among the citizens, right? And from the second week, we introduced the digital intervention. We give them all the information, right? So that they can understand. And the third week was continue with this, right? And after the third week, we conducted the semi-structured interview with the participants, right? So from the data, it has been observed that since we introduced a digital intervention, there was a significant change in their behavior. That's the overall change we found out from the data we collected from the IoT devices, the calibrated IoT devices, right? And also a change we found out in terms of their indoor activities. You can see from the data the amount of ventilation they have used before the introduction of the digital intervention and afterwards, right? So it shows the significant impact change in their behavior, and that influence that helped them to raise their awareness about the indoor air quality. So, in a nutshell, what are the key takeaways and what we have observed? So, the IoT enabled real-time air quality monitoring device and the citizen awareness, right? So that device we calibrated that helped them to collect the data, help us to collect the data, and show in a way that help them to understand their indoor air quality. If you show them just the data, that's meaningless. But if you give them a context that what you can, if the level goes up, what steps you can take, for example, opening the ventilation, that help them to reduce the indoor air pollution level, right? So it's AI driven insight and a personalization. If in a future research, we are thinking of to apply, we are thinking to use the AI, how we can use how we can send them the personalized messages, for example, based on the level of the indoor air pollution and the activities they are doing, right? So and also the trust in the technology, it's essential. As I said about the information you are disseminating to the participant, that is most important. How you engage with them and how you disseminate the information regarding the study. And also the promote the community driven approach, as we did. We engage with the local communities for these studies, right? And this observatory helped to achieve the net zero emission and sustainability in the cities, right? And improve the indoor air quality and have the better health outcomes. For example, reduce the respiratory disease and the fewer hospitalizations. So in a way, if the citizen get awareness about how they can improve their indoor air quality, right? So it will help them to improve their health conditions as well. So these are some of the research outcomes we have published, and yeah, thank you for your attention.
Thank you, Rameez. It was well within the time. So we have some time. I'm hoping that people will come up with questions. Let me start. I have a question, first of all, Rameez. So it's first of all, very good work. I really liked it, and the outcome is very fruitful, as we can see. I was wondering sorry if I missed it. I was wondering if there is a way to know what is the cause of the quality issue, right? Are we able to provide that information to the participants? So, for instance, we can see that they have made changes in activities, yes. But is it possible to say from our models that a certain activity is actually leading to this problem? Right?
It depends upon what activities you are actually measuring. For our study, our main focus was on the ventilation. Like, for example, the amount of ventilation they have. So we asked the question that how many hours you are opening window during the 24-hour time period, right? So it was a generalized question. It was not a specific window. We asked them that are you opening between 6 to 10 or 10 to 11, right? So if we can ask this sort of personalized question, then it can help us to link with the air pollution level during that time, right?
Right.
So in a way, it will help them to understand more. But generally, in the testimony, when the participants say that whenever they do cooking or anything, or they see the smokes inside, because whenever you do cooking with it, because some of the participants were Asian, so we are Asian, we love cooking, right? And we use the oils quite a lot in all the dishes and everything, right? So they have admitted that whenever say there's a smoke, they trigger them. Let me see the air pollution level, and that what we want actually to this is the activity there. This is the activity they're doing, and that causing the spike in the air pollution level in PM 2.5 PM 10, right? So if it is more specialized, it would be very helpful for them to understand, yeah, and for us as well. that how we can
so I
this
was
window.
Yeah, I was wondering some amount of causal or explainable stuff will actually help us here more in
Yeah,
providing that information back to the user. Or I think there is also scope for other kinds of works to be linked here. For instance, human activity recognition from
yeah,
various sensors, or if we are talking about a smart building, we can have CCTVs to analyze what is going on. So this can be actually paired with your monitoring to say that, okay, this is a particular activity that actually led to this increase. Maybe it's just a thought.
yeah.
So
No,
maybe,
that's a good thought actually, because we also thinking about the when we are talking about the, mechanical ventilation. Some of the studies I've seen in the past that they put these sensors next to the windows, that how broad they are opening the windows, or what sort of door size, what sort of size of the window they have, and so this sort of activities also help to feed back into the loop and help us to understand what else we can do to make for the better improvement.
yeah. Thank you, Ramesh. So Will has a question for you. Will, do you want to ask it yourself?
Yeah, sure, that's fine.
Yeah.
So thanks for the talk. It was really interesting. So I've got an impossible question, really. But I'm a bit obsessed with wearables at the moment. I think the future of healthcare is really going to be more devolved and distributed outside of hospitals, in the home, things you wear, things like that. So I wondered whether would it be feasible to build in some of these air quality sensors into a wearable, whether it be a smartwatch or something else. Because it would be really cool to have like a mobile sensor on your body, giving you continuous information that we can take indoors and outdoors, with also the
Yeah.
psychological nudges as well.
Yeah. That's a really good question, but based on the literature and the study I did in the past during my PhD, when you move the sensor too much, you will not get the accurate data. That's why if you see most of the air quality monitoring sensors are stable, or put it at a standalone, so that it can monitor the data very well. If you move too much, then that again it has the impact of the air flowing through the sensors. Our human body temperature, that again influence the temperature sensors performance, right? So these sort of things also we need to think about.
Yeah, I thought it would be a difficult problem.
Yeah, it is. Yeah,
The other
because
thing
some
I
of the
was
schools they have conducted this sort of studies. They put they give the backpack to the students and with the sensors on mounting on top, right? But you will get the dynamics. You can't get the exact the value of the pollutants, but you can get the dynamics. For example, the range of 10 to 20 microgram per meter cube. But you can't say exactly this was the at certain time the 12 microgram per meter cube was the reading by the sensor.
Yeah, so it's potentially possible in the future.
In
The other
future.
thing, maybe just one comment I'll make is you mentioned about Gokul, about tracking, trying to understand what the causes of the air quality, but then there was some discussion about security cameras. It made me feel a bit Orwellian, like Big Brother. So I just thought I'd flag that as an ethical.
Sure,
Yeah.
sure. Yeah. I think, like in India, you have like cameras in public places, but not exactly like prying on the privacy, but rather like on the street or on the corridors of building, something like that, rather than inside the homes. So, and I'm sure like office spaces we are all monitored very well, I would say. So, office spaces, I think commercial spaces have more of these problems, what Rameez has been telling about, right? The air
Yeah.
quality issues. And I am sure we all remember the COVID times when we were not supposed to use air conditioning and things like that, right? So, which actually leads to one more question if Will is done. Yeah. Okay. So, Ramesh, I had one more question. So, considering the health of people inside a building or a room, right? So, the air quality index can, I'm actually a noob in this area. I'm not much aware of what can be detected from the air, right? So, from the environment, is it possible to detect foreign particles or, something like let's say if some infection is around, people are able to get it, right? So is there any correlation between air quality and something virulent in the air in a room?
Uh, uh, if I want to give you the answer, for example, the device we use, sensor STS011, that monitor the PM 2.5 and PM10. The mechanism of that sensor is using the laser infrared, right, to detect the
Okay,
particle size of that.
right.
Similarly, for detecting the disease or virus in the air, it depends upon how you are identifying them. For example, the blood test, you take out the blood test, right? And then you
Right.
find out that there is a disease or this sort of
Yeah.
bacteria in your blood, we found out. So if you have the sensor, right sensor to detect, right now, I'm not sure about how they detect from the air, but this could be possible, but depend upon the mechanism of the sensor.
Sure. Okay, cool. Yeah.
Like
It was just a sci-fi question.
yeah. No, that's a good question actually. If you see the nitrogen tube outside for the monitoring NO2, right? So there isn't
Right.
any sensor. They deploy the tubes, fusion tubes outside of the road, right? And they collected every like bi-weekly or monthly for that samples, and then they evaluate and then they measure that what was the level of the NO2 during that time period, right? So so this sort of things happening in this domain, yeah.
Sure. Okay. If there are no more questions, uh, okay. Thank you, Dr. Rameez, for your wonderful talk. So let me move on. So Taofiq, assuming you are here, can you hear me?
Hello, good afternoon. Yeah.
Oh, hello.
Can you-
How are you doing?
I'm good. Good afternoon.
Yeah, sure. So let me just quickly introduce you. So I welcome, forgive me if I'm pronouncing it wrong, Taofiq Adeyemo.
That's
Uh, yeah. He's a PhD student in DAIM at the University of Hull, and his projects currently involve development of machine learning medical diagnostic to predict brain bleeds in glioma cancer patients. He's also working on responsible AI frameworks on healthcare. So happy to have you here. So please go ahead.
Oh, thank you very much. Let me quickly share my screen. Can you see my screen now?
Yes, yes.
All right. Thank you very much. Good afternoon once again. My name is Taofiq Adeyemo. Today, a PhD student at the Center of Excellence for Data Science, Artificial Intelligence and Modeling, University of Hull. So today I'm going to be walking you through our recently conducted systematic literature review of explainability and stakeholder engagement within responsible AI frameworks in healthcare. This is in a bid to try and find a solution or at least identify the reason for a problem that has been lingering in literature a long time ago. The plan is to talk you through the background and the problem itself, then our aim, then the methodology that we adopted. Then we'll be discussing our results and finding. Then we'll conclude this presentation. Now, when I go to the background, we all know that artificial intelligence has the capability to revolutionize any field at the moment. They are fast growing and their impact is being felt across majority of the fields that exist today. But their integration into sensitive sectors like healthcare calls for a careful consideration So we say that before AI model can actually be adopted in sensitive sectors like healthcare, then they must be built upon responsible AI principles, which are principle of fairness, which says that all the involved parties must equally be catered for by this AI model. Then transparency says that the internal working and the prediction mechanism of this AI model must be understood by all the stakeholders involved. Then the third one, which is accountability, says that AI model developer must be responsible for the impact that this AI model has made in their field of integration. Then privacy, it's saying that all the sensitive information, private information that goes into the development and operation of this AI model must remain private. And safety says that this AI must not cause any harm to those people who are going to be using it. But despite the fact that we have all these principles out there, why is it that we still have a limited adoption rate of this AI in the healthcare sector? So this now takes us to the problem statement, which according to Tim says that despite AI transformative potential in healthcare, the adoption of responsible AI remains limited. And Sierra 2022 said that this can be attributed to transparency concerns. Transparency here means that the stakeholders in health are actually finding it difficult to understand the working, the internal operation of this AI. They are finding difficult to understand their predictions and how they are working. So that is what Sarah is trying to say here. So this makes us to look into this direction as well. So we want to look at why transparency is a problem. So this takes us to the aim. We want to find out why responsible AI are not being adopted in literature. And as a result, we conducted a systematic literature review. And we focus on explainability and stakeholder engagement. These two elements, which is explainability and stakeholder engagement, are being focused because they are very important when it comes to model transparency. So that is why we are looking into that direction. The methodology, this review, because this is essentially a review, we can't afford to just cherry pick. It has to follow a method. So we chose to conduct a systematic review for at least so that this project, this review can be reproduced or can be followed up with other subsequent review, or at least we can verify the outcome of this review. So we chose to conduct a systematic review, and let's quickly talk us through some of the protocols that we used, the review protocol. The research question that we used was, what are the key challenges and best practices in implementing responsible AI frameworks in the healthcare sector? And the keywords that we extracted from this question were responsible AI, artificial intelligence, then a framework. So we use these key terms to construct our search string that we use to search Scopus, a Web of Science, MBase, and Medline database. This is the Prisma flow diagram. After we conducted our literature search, we were able to identify 257 articles. And after the removal of duplicates and screening, we identified 8 articles that has a framework in them. This now takes us to the extraction table. We have this table. The first column is the author of these articles, and the second one is the title. Then the third column is is talking about the stakeholders that we were able to identify within these frameworks. And the second to the last, the next column, which is stakeholder engagement gap, is talking about if there's any a gap that we identified while trying to go over stakeholder engagement in these literatures. And the next one is ME, which is talking about if this framework actually has a section that talks about explainability, because we come across some frameworks that do not talk about explainability, so those were screened out. The next one is MSE. We want to know if this stakeholder actually make mention of stakeholder engagement as important or as key to achieving explainability. And the last column is trying to see if this framework actually says that stakeholder actually provide a structured guideline for engaging this stakeholder. So this is how we come about this extraction table. So this takes us to the result section. The first thing we did was to analyze identify key stakeholders across these frameworks, and we grouped them into category. Then we plotted these charts, and there was an interesting insight from these charts. This insight, we can see from this chart that some stakeholders are actually more popular compared to others, which means that some stakeholders are being potentially underrepresented in these key frameworks. And the implication of this is that if these stakeholders are underrepresented, then during AI model explanation, then their explainability need might not be catered for during model explanation. And if it is not catered for, this might be one of the reasons why these final models developed without catering for them is having problem when it comes to transparency. So, this final model will not take care of the explanation need in its explanation. So we suggest that there should be a kind of guideline or at least a checklist that will assist AI developer in identifying all the stakeholders that are relevant to their AI project before they commence the explanation process of that model. From here, we go to the next finding. So if you look at the two green boxes about explainability and stakeholder engagement to the right of this slide, we will see that all these frameworks unanimously agree that explainability and stakeholder engagement are essential for transparency in responsible AI. But the question is, why do stakeholders still struggle with trust and adoption? So this suggests that explainability and stakeholder engagement alone aren't sufficient to achieve true transparency or trust. So this supports the gap identified in our review, which is the absence of structured guideline for effectively integrating these two elements, which is a crucial gap that none of the identified frameworks address. And we know that without structured guideline for stakeholder engagement, AI model developer, or let me say the AI model risk lacking relevance or may overlook essential aspects of stakeholder input because what the developer will resort to is using a sporadic, inconsistent engagement approach. And this might mar the whole essence of stakeholder engagement. Then this may not get adequate or enough facts from the stakeholder to ensure that the model is okay logically or technically. Then it may not translate the model. The explainability of the model might not be well addressed if we do not get enough question or enough insight from the stakeholders. So as a result, this might lead to model with explanation that is overly maybe technical or lack clarity, which might limit stakeholder understanding and failing to meet the diverse need of the involved stakeholders. It may also lead to misunderstanding about the model. When it does not meet the expectation of the stakeholder, then they might not be able to understand its whole essence, why it has been developed in the first instance. So together, all these issues determines undermine stakeholder trust and acceptance, thereby reducing the likelihood of successful adoption. So therefore, developing structured evidence-based guideline for stakeholder engagement could bridge this gap, in our opinion, and improve the adoption and reliability of responsible AI in healthcare. Let's now move on to the conclusion section. Here, we want us to we want to remind us that effectively involving stakeholders in AI model development is not a straightforward task. We can say it is a science on its own and involves a systematic approach and rigorous effort. Then we also have to understand that majority of the time, the primary responsibility of these stakeholders lies outside this AI project that we are creating. So this makes their engagement without disruption to their own primary work a nuanced challenge and calls for an optimized route of engagement that maximize the little time that we want to spend with them. So this need for thoughtful engagement highlights the need, the importance of a well-designed framework where clear evidence-based guidelines to optimize their involvement is clearly spelled out. So such a framework is essential not only to achieve a good technically sound model, but also to it's very important in embedding transparency and tailoring explanations to meet the diverse need of different stakeholders that is involved in this AI project. So this through this structured approach, then we can potentially bridge the current gap in responsible AI in healthcare, therefore leading to the creation of more models that are truly explainable, trustworthy, and aligned with the ethical demands of modern AI applications. Finally, we want to say that we need a standardized guideline for all stakeholder engagement to have a chance at resolving transparency issue that has earlier been identified before we conducted this systematic literature review. These are our references. Thank you very much.
Thank you so much, Taofiq. So I would request everyone to post their questions on the chat. So meanwhile, Taofiq, I have a question for you. So we have seen all the advantages of bringing together so many stakeholders while maybe building and deploying an AI model or a system, right? So, but have you seen any disadvantages in that?
Please, I didn't get the last part of the question.
Have you seen any disadvantages in involving so many stakeholders while building a solution?
Actually, the first challenge in engaging stakeholder is that we have a lot of stakeholders that are out there. Then, for you to identify all the stakeholders, that's a challenge, number one. Then, secondly, when we're talking about explainability and stakeholder involvement, there's no how you. It's a challenge to actually tailor the explainability of your model to meet all the requirements of the stakeholders without affecting the effectiveness of the model that you have created in the first instance. So that's one of the disadvantages of trying to tailor explainability to meet the need of all the stakeholders. It might affect the effectiveness of your model.
Right. Thank you so much. So I have one more question. So I might have missed it, but have you thought about providing weightage to the role of the stakeholder for a particular phase in design?
Please, do you want to take that again?
So have you considered providing some weightage to the role of the stakeholder during the particular design, right? So for instance, for a healthcare application, some phase of it will require inputs from the doctor, but whereas some phase of it will require input from a lawyer or a social scientist, right? So have you considered weightage for these opinions that are coming in during the stakeholder engagement?
You mean, do I have a weight for this opinion that are coming in?
Yeah, so for instance, at some point, the weight of the doctor might be much more than what a computer scientist is saying, right? But at some point, when we go to the core AI development, the computer science person should have higher weightage than any other expert. So have you considered anything like that?
Actually, during this review process, we are only trying to focus on creating the guideline. And
Okay. Okay.
It's not, all the stakeholders are considered to be important when it comes to explainability, because that is
Right.
what we're looking at, and their opinion must count when you are developing this explainability need.
Okay. So just for FYI, right? So Center for Responsible AI at IIT Madras has put forward something called Participatory AI Design Framework. So maybe you can give it a read and tell us some feedback as well. Right.
All right.
So yeah. So thank you so much. I think I'll ask Professor Dhaval. He has a question.
Okay, thank you.
Hi. Thanks for your presentation. Maybe I missed or misread. You had a slide which says 0% existing work focuses on providing guidelines for stakeholders, or misread that?
Yes, sir.
What I'm trying to find out is whether you say there isn't work which focuses on providing guideline for stakeholders, or there aren't many work. There is a research gap. Yeah, 0% provides.
Yeah. Majority of these frameworks, they said that involving the stakeholders are very important, but they do not provide a guideline on how to actually engage the stakeholder and involve them in our work.
Okay. All right. But leaving the percentage out for a second, any thoughts on why it's so low in terms of the priority of this responsible AI frameworks?
The number one thing that I would talk about is that responsible AI field is a little bit new, and we have little frameworks that has to talk about frameworks that can be used to implement an AI responsibly. So that is why we have very few frameworks out there that addresses a responsible AI implementation. Probably that is why we have low percentage of framework talking about how stakeholder can actually be engaged while implementing explainability.
Okay. And may I just add, I don't know whether there are any other question, but do you think that there is something for us to learn from how the software engineering field has evolved? Because there are a lot of software engineering frameworks and methodologies which heavily involve stakeholders in design of an artifact. And I'm wondering that there is a field we could look into, which has been around in a mature way for last 30 to 50 years, to learn and adapt from how they have done things.
In health sector, it's very in health sector, if you want to develop AI model, then there's no how you will not engage a stakeholder and get an AI model that can actually be adopted. So if you say you have a lot of frameworks out there for software engineers, then they can only lead to the creation of models that are technically sound, but when it comes to transparency, they might not be able to address the need of the involved stakeholders, and they might not be adopted eventually.
Okay, thank you. We can talk offline, but there are other questions, so you might want to take that. Thank you.
Sorry, Taofiq, there are 3 questions. So Chitralekha is asking, what criteria should be taken into account in order to identify the most suitable stakeholders for healthcare?
In order to identify the stakeholders, then you have to, first of all, look for a focus group, or you create a survey, or you organize a workshop. And then there you'll be able to identify all relevant stakeholders for your AI project.
Cool. So John Carrick has a question. Healthcare workers' first priorities will be always the people they look after for, the patients, residents, etc. So do you see a solution for encouraging them to try out and adopt new AI technologies?
Do you want to take that again, please?
Sorry, Taofiq. Sorry.
I want to take that question again.
Okay. So healthcare workers' first priorities will be always the people they look after, the patients, residents, etc. So do you see a solution for encouraging them to try out and adopt new AI technology? That is the question. It is there on the chat. You can.
AI technology for explainability or to create an AI model. I want the person to elaborate.
So, sorry, Taofiq, I missed it. Sorry.
Is it AI technology for explainability approach or to create?
I think it's more like generic. The question is more generic. So it's about just getting people to try out AI technology, right? So is there a solution for encouraging them to try this out is the question.
Yeah, it does. AI field keeps evolving. If there's any better approach to getting the explainability process right, then it's welcomed. But if there's no other approach, then we keep on using the available explainability needs. But what we are saying here is that no matter the stakeholder, then their explainability need has to be catered for. And before you can be able to cater for the explainability need, you have to engage them to know how you want, how best they can understand the internal working of this AI model, so that their need will be satisfied.
Okay. Yeah. Okay. So John, if you have any follow-up for that, you can maybe type it out, and Taofiq can take it afterwards. Last question, Taofiq. So Bhupesh, Dr. Bhupesh has this question: how do you manage judgmental bias in the guideline? So I think what he means is that different people will have their own judgmental biases about the system, and they come in and be participatory in nature, right? So is there a way to handle it?
If this review is actually looking at explainability and transparency, we have less focus on fairness, which might be talking about bias.
Okay.
Yeah.
Okay. Yeah. So maybe Bhupesh can take it offline with Taofiq. So with that, I think there are no more questions. So thank you, Taofiq, for the wonderful talk. Thank you. So I'll move on. So the next speaker, as per the schedule, is David Molyneux, but unfortunately he could not make it as he's not well. We wish him a speedy recovery. So I would now go on and welcome Dr. Krishna Pillutla. He is an assistant professor at Wadhwani School of Data Science and AI at IIT Madras. He's also one of our lead faculty principal investigator at Center for Responsible AI. He and his research group study theory and practice of machine learning and AI, and his focus is on privacy preserving and robust learning of LLMs and generative AI with applications to healthcare and public good. So Krishna, very happy to welcome you for the talk here. Please go ahead.
Thanks, Gokul, for the kind introduction. Let me share my screen. Can you see my screen?
Yes.
Okay, and the slide change as well?
Yeah, good.
Okay, fantastic. Okay, so thanks, Gokul, for the kind introduction. I'm Krishna. I'm faculty at the Wadhwani School of AI. And the topic of my talk today is to figure out whether my data was used to train a large language model. So broadly, I'm interested in questions of privacy. And this talk is not directly going to be related to healthcare, but some of the considerations of privacy are quite relevant there. And in fact, I've recently started working in the domain of healthcare, but early days to talk about anything on that front. So I'm just going to talk about large language models. Okay, so this XKCD comic is quite witty, but and you might have seen it years ago. So it's remarkably prescient because it came out in 2019. And if you think back, ChatGPT, which sort of took AI to the general public out of the technical circles and to the general public, actually only came out in December 2022. And GPT-3, the model which powered the initial version of ChatGPT, came out in mid 2020, right? So this came out in 2019. So it predated all of them. And it actually correctly identified that language models might actually leak information about their training data. And soon after, about a year or so later, researchers caught up and showed that this is indeed the case, right? And not only do language models leak information about their training data, they do so very reliably with a very high extraction rate. So a large amount of the training data can actually be extracted by someone who wants to sort of mine the data out of the model, right? And this is quite concerning. But there's no reason to hate on language models alone. This is true for other kinds of generative models, such as image generative models, as well as this paper shows here. So whenever we start training these big models, particularly generative models, we need to be very nervous about what data is used to train them and how privacy sensitive the data is. But for a quick moment, let's set aside these privacy considerations. Let's suppose we have some target task and we want to train a model to do well on that task, and we are free to go and collect the data that we think will be appropriate for that task, right? So what data would lead to the best possible performance in some downstream task? This is again like a research question which is very well studied. The answer is not surprising. It's train on whatever domain you expect the model to be deployed in, right? There's a huge body of work that says, if I train my model on one particular domain and I test it on another domain, the performance degrades from the training domain to the test domain, right? This is this so-called robustness gap. And this is reproducible across model sizes, across model generations, across modalities, and so on. So this is actually like a fundamental property of these machine learning models. So in summary, the best training data we want to use, if we only care about the downstream task performance, is this in-domain data. And for a lot of applications, let's say in healthcare, we have a bunch of chest X-rays, and we want to predict, tuberculosis or pneumonia, and for instance, from the chest X-rays, right? So all of this data comes from some person. So multiple data points that we collect would be associated with a particular real individual, right? And this is also true in other sorts of scans, brain, retina, skin, and whatnot. So the fact that there is an underlying person makes this data quite sensitive. And this is also true in other domains apart from healthcare, right? For example, we take all of these language models like ChatGPT or Gemini or Claude. The idea is that when these models are deployed, the kind of user interactions that they are subject to is the best data that the models should be trained on. But then that data is sensitive user data, right? This is also true for predictive tools like email writing assistants or general AI assistants like Copilot, right? All of this user interaction data is actually is very sensitive. So the in-domain data that we actually want to use is user data. And there are many challenges associated with using sensitive user data. The one that I'm going to focus in particular on is that each user can contribute multiple examples, right? So say OpenAI wants to train a model based on my interactions, and each chat of mine, each interaction of mine with ChatGPT is one example. And because I have some data, potentially some information about me, which is spread across each of these interactions, someone can put them together, right? And that introduces an additional privacy risk. This idea in general is again not new. It is called a linkage attack and has been studied for at least 25 years, if not more, where you combine data from multiple sources and learn something more about the individuals, right? And by the way, this is also turning out to be quite a serious issue in the healthcare domain, where we need serious, robust anonymization techniques, right? So the aspect of using multiple examples to train a model that I'm going to focus on today is more related to training models. So was my data or was any particular user's data used to train a given large language model? And with models these days, they are not usually trained from scratch, but we get these general purpose pre-trained models, which are then fine-tuned on specific tasks. So I'm going to focus on that fine-tuning step. So let's suppose that we have a bunch of user data, and we fine-tune a model on this data. So the task of finding out whether a certain user's data was used in this fine-tuning process can be modeled by an adversary who is then given this fine-tuned model and can query that model, and now has to guess whether this particular user's data appeared in training or not, right? One key aspect here is that the samples that the user has contributed to training might not coincide with the samples that the adversary or the attacker has access to. If we go back to that email example, some of my emails might be used by Gmail or Outlook or whoever to improve their models. But then an attacker may only have access to some other emails that I sent out on, say, public mailing lists, for instance, right? And those might not coincide with the exact examples of mine that were used in training. So that distinction is key here. So to formally state the threat model, we call this a user inference attack. Starting with the top right on the screen, we have a model which is fine-tuned on data which comes from a bunch of users. Then to the bottom left, an attacker has access to this fine-tuned model and a bunch of fresh samples, right? Not the same training samples, but a bunch of fresh samples from a given user. And the attacker has to guess whether these samples came from one of the training users. The exact attack is actually very closely related to something that appears in the literature already, so I won't go over these details very carefully. The key idea is that we look at each of the examples that the adversary has access to from a given user and looks at how likely they are under the fine-tuned model, comparing that to how likely such an example would be on, let's say, a general pre-trained model. And if the example is significantly more likely under the fine-tuned model on average, then the attacker would guess, yes, this user's data has appeared in training. So moving on to some plots here, we have some experiments from 3 different data sets. So these plots show histograms. The attack that I just described has a certain test statistic, and the attacker looks at this number. It's basically a number and guesses whether this user was in or out, right? So if that number, the test statistic, behaves differently for users that participated in training versus users that did not participate in training, then the adversary can make an informed guess about whether that user's data appeared in training or not. So this blue histogram is the statistic for training users, and the orange one is the statistic for users that did not appear in training. And the more distinguishable those two histograms are, the easier it is for an adversary to guess whether the user appeared in training. So across 3 data sets, what we find is that if we have more number of users who contributed data to training, it's hard to tell whether a particular user appeared in training, right? So that's a phenomenon of hiding amongst various clones. And on the other hand, if we have a user who contributes a large amount of data, then it's very easy to guess that users' participation in training. The way to summarize these histograms is with an ROC curve, and one number that we can use is the area under this ROC curve. The larger it is, the better the attacker does at guessing whether user is in or out. So the next plot is about the worst case. So it may so happen that the attacker is not able to guess on average when a certain user appeared or not, but if the attacker can reliably guess that, let's say 10 users' data appeared in training, right? Or 1% of the users, if the attacker is very good on that subpopulation, it's already a very severe privacy risk. So with privacy, we often care about the worst case. And one way to model worst case is to have artificial water examples that are known as canaries, right? So here we have real examples, and we insert common substrings across all of the examples from a certain user. And once we start doing that, the success of an adversary at user inference jumps way up from something like 0.6 AU ROC to all the way up to over 0.9, right? Which means it becomes very easy for an adversary to guess if there are these common features, which, for example, can be email signatures, right? So in my emails, if I have my name and designation and whatnot, that is a common feature that is shared across all my emails. So this next plot is what explains the mechanism behind user inference. And it's directly related to overfitting. So this slide is a little busy, so let's try to break it down. This blue line is the success of the attack, right? So as we keep training, the attack becomes more and more successful. This is the blue line, the AROC going up. Now, there are 2 other lines. The orange line is the validation loss on users whose data was used in training, right? So how well does the model make predictions on some other emails of mine which did not appear in training, right? As opposed to the emails of someone whose data was not used in training at all. So that's the green line. Right? So if you just look at the orange and green line and ignore everything else, it's a textbook example of overfitting. So the orange curve goes down while the green curve goes up, right? Except the orange line is data that did not appear in training at all, right? So it's data from the same training users, but the exact data used to compute this orange line did not appear in training. So really what's happening is the model is not overfitting to the training examples, but it's overfitting to the training distributions of the users, right? So it's capturing the common features that appear across the multiple examples of a given user, and it's able to capture those very well. So that's where we see this sort of divergence between the orange line and the green line. And in fact, that correlates very strongly with attack performance, right? So this explains how user inference attacks take place. So can we actually mitigate these attacks? we tested out a large number of heuristics like early stopping, gradient clipping, which just don't work at all. We can deduplicate data, which is a natural thing to do, but it does not solve the issue. We can impose data limits per user. That is helpful, but if we don't have a lot of data, we can't go about discarding data. So its practicality is limited. One that I wish to talk about for the next minute or so is differential privacy. So essentially, differential privacy is a provable guarantee that says if we look at our algorithm, which takes in our data and produces a model, that model doesn't change a lot if we add some additional data, right? So one additional unit of data. And this can be fully quantified by how much does this distribution change and in what metric, right? So all of those are details. And usually one takes this example, this unit of data that is used to define differential privacy as one example. But as I mentioned, a user can contribute multiple examples, right? So that's a caveat that we need to evaluate here. So going back to this example of memorization that I presented at the very start, it turns out that example level DP, or DP stands for differential privacy, actually does eliminate memorization, right? So the left plot shows that in terms of the loss, we are nearly as good as the non-private one, whereas the memorization plot on the right shows that there is significantly improved memorization behavior compared to the baseline. So coming to user inference, which is the problem that I'm interested in, it turns out that differential privacy really does not help very much here. In particular, it does not help in the regime where the adversary does not want to make many wrong guesses, right? So the case where the adversary has a small false positive rate, in that regime, example level differential privacy is just, it doesn't really do much better than not having any differential privacy at all, which is this green line, right? And in addition, there's a big hit to the performance of the model. So really what we want to do is to take differential privacy at the user level, right? So whether or not I remove all of the data corresponding to one user, we get good performance. And this is challenging because there are a lot of systems issues which show up when implementing it, right? Because large language models are huge and anything we do needs to be very optimized, and we don't have the right kind of software support to implement something like this in general. But but if we could, then differential privacy actually gives provable guarantees that user inference is not possible, right? The caveat here is that the differential privacy should be at the user level. But to overcome these systems issues, we've had some recent work. This is a very recent preprint, and this getting differential privacy to work at the user level at scale is a challenging question, and one that I've been working on for a bit. For example, with these two papers, we've had some advances in differentially private training. And in fact, one of the approaches proposed here is used for Google's production language model, and it outperforms. It's the mustard green line which outperforms the previous production system in orange. So we are getting to the point where user level differential privacy is close to being practical, but there is much work to be done there. And with that, I'll conclude. Thank you. So this is work which was led by an intern, Nikhil, when I was still working at Google, and with a bunch of other collaborators. And this paper will be an oral presentation at the MNLP conference later this year. Thank you. Happy to take questions.
Thank you so much, Krishna. So folks requesting to please post questions on the chat. So meanwhile, Krishna, if I can poke your brain with one question.
Please go ahead.
So the differential privacy thing which you stopped with. So can you maybe, for the sake of the audience, tell like an example how it might work in a healthcare setting?
Yeah. Yeah, so that's a very so differential privacy is very well studied, right? The basic idea is that so going back, oops, sorry, I went too far back. Yeah, whether or not you have this extra orange example, the model that you get at the end of training doesn't differ by very much. So that's the guarantee. And the way to enforce that guarantee is to make sure that, so you do two things, right? The first thing you do is to make sure that each example can only have a bounded impact on the model. And the way you enforce that is by clipping your gradients, which is something that we do anyway for the sake of robustness. So you clip the gradient obtained from each individual example to a certain norm, right? So if my prediction is so bad, the gradient can be so large that the presence of that one example can actually alter the behavior of the model in some region of the space, right? So clipping the gradient prevents such a thing from happening. And the next thing that you do is you add noise. So you run your stochastic gradient descent, you clip your gradients, and then you just add noise to your gradients. So what adding noise does is it gives plausible deniability. So because there is noise, you can't say for sure whether this particular behavior is because there was a gradient that made you take that action or just purely because of the noise, right? So in practice, what you would do then is you train a model on your data, healthcare data, and you just change the training procedure. So the key, of course, lies in the details. So to make differential privacy work, you need to have you need to use the right, so you need to know which data is considered private and which data is considered public, right? So if your data comes from, if you have images on the internet, why would you add noise and degrade the performance of the model? You might just use it as is. Whereas if you have, let's say, interactions between doctors and patients, you would treat them with the utmost seriousness, right?
Exactly. Yeah. So, which actually leads to one more question. So, with these techniques that we apply in very critical sectors like healthcare, do you think there could be trade-offs, like with respect to the efficacy of models?
Yeah, of course there. So that is the main issue with this, right? So you don't get privacy for free. So why do these models work? These models work because there is some data on the basis of which they're able to change their behavior. Now, it turns out that deep nets do so by memorizing the data, which is bad from a privacy perspective. So now if you want to stop these models from memorizing the data, you're fundamentally altering the mechanism in which they work, which means you will get some degradation in performance, right? So the question often is this hit in performance commensurate with what you would gain by protecting the privacy of certain data, right? So in an ideal world, you would have privacy protections and you would have good performance, but in reality, there's a trade-off between the two. So you, as someone who's building these models for a specific application, need to find like a sweet spot between the two.
Right. Sure.
And
Thank
there's
you.
no like one answer that fits all, right? Like this is a very specific answer, and sorry, it's very application specific. And a lot of these techniques that I've sort of hinted at in better training and so on can push the boundary a little bit, but it does not circumvent the fact that there is a fundamental trade-off between the two, which you need to answer.
True. Okay. Thank you, Krishna, for answering my question. So there are like 2-3 more. So Omer has a question. Given that there might be several players in the value or supply chain for an AI tool that is being deployed for people, how do you place accountability in instances of data leaks, data erasure requests, or is there a need to rethink privacy laws for AI?
Absolutely. So this is a very complex question, and the short answer is that privacy is multifaceted, right? So there are many aspects to privacy. What I described here with differential privacy concerns one very specific aspect, and that is anonymization, right? Was my data used in it or not, right? Meaning, am I anonymous to the model or am I not anonymous to the model, right? So I very specifically looked at anonymity, whereas there are in the model training, but there are many other things in the pipeline, right? So how is the model trained? Where is it trained? Is the system in which it's trained secure to hacking, for example? Is data going to places where it is not supposed to go to and from where someone can hack it and extract it, right? Is privacy here, does it align with what a normal common end user would interpret as privacy? So all of those are questions that need to be answered. And none of them are answered by anything that I talked about. I only focused on the question of anonymization. And if it comes down to, actually deploying the system, all of these other things are very much important. So in short, yes, I do think we need to have like comprehensive privacy laws in place, which there are in some jurisdictions, like the EU has some, but I think we need more of those, and we need more stakeholders in coming up with those laws as well, because some of them may not exactly map to reality. As in, might not be feasible for a real system to satisfy some of those laws because it's just technologically impossible, right? So we need to make sure those laws make sense, are semantically meaningful, and like allow innovation, right? So this is a very complex question, and I don't have an easy answer.
Sure. Thanks, Krishna. So I will take one more. There are two questions, but maybe Krishna, you can answer one of them by replying in chat later.
Sure.
So I'll take Dr. Bhupesh Mishra's question. Do you have any selection criteria for the noise or random noise that can be used for the TP?
Yeah. So this is something which has been quite well studied. Basically, Gaussian noise suffices, but any noise that you take has some sort of privacy properties. But we usually end up using Gaussian noise because it's the best behaved. Yeah.
Right. Yeah, I think this. I'll just take this last question.
I'll just complete that answer. The key is what is the standard deviation of the noise, and that's where a lot of research goes into, right? How much noise to add. So yeah, that's where a lot of work is necessary.
Great. So the last question by Julius. So if my data was used in training an LLM, do you think an AI-enabled chatbot built with LLM will pass my personal data to users of such chatbot?
It's possible. It's possible, but all of the creators of these chatbots try their best to prevent that from happening. But right now, we don't have like a comprehensive solution short of differential privacy, which, as I described, is still a work in progress, right? So what people do now is to put like band-aids over chasms, right? So there's a really fundamental issue with these models, which is that they memorize data. And the way service providers sort of patch it over is by saying, oh, don't respond to queries of this sort, right? Which is very easy to break. So it is possible. And it's a cat and mouse game between people trying to break these models and model developers. What I would really, really, really like to see is some, solution which is by design immune to these kinds of issues, which needs a lot of research, and that's one of the things I'm working on. Yeah. So to answer the question, it's possible, but it's not. It doesn't happen all the time. The way things are.
Thank you, Krishna. So for the very nice talk and very insightful answers. So with that, we have come to the end of this session. So we would now have a coffee break, have coffees at your respective places, and we will convene back in exactly half an hour. So we have to begin the panel discussion. We have a very interesting panel. We have a panel discussion sharp at 4:45 p.m. Indian time. So please try to join like 2-3 minutes before the panel begins. Okay.